A dumbass here forgot to press record. So we'll go through this. I won't go through it too slowly because you can pause it and write in the bits. So what we had here was light beam spans 6 meters, simply supported at its endpoints. We've got a UDL between 2 and 5 of magnitude 72. That doesn't go to the end of the beam, so we will have to turn off the UDL. It says express the bending moment in terms of step functions by solving this little equation here. I recommend strongly always drawing a little picture. So we drew a little picture, and it's a UDL that must be turned on at 2, and that's with a plus, and turned off at 5 with a minus. So now what I recommend is you write down m double dash is minus this. Now minus something, maybe we'll just write this down. It's something improved. Minus w of x is minus 1 times w of x. And imagine multiplying this by minus 1. So it'll be minus 1 brackets this. You'd have minus 1 times this and minus 1 times this. The minus 1 times the plus will give you the minus, and the minus 1 times the minus 1 will give you the plus. So that's why these signs kind of flip. But in the first instance, I mean, how do you do a UDL? This is what we did a couple of lectures previously. You do turn it on with a plus, turn it off with a minus. Okay. So now we're this far, we anti-differentiate both sides. So you go from the second derivative to the first derivative, fix the constant, antiderivative u square bracket, fixed constant, antiderivative u square bracket, and we pick up a constant every time we antidifferentiate. In this, the first one is Ra. And we go at it again. You go from the first derivative to the function, fix the minus 72, and the antiderivative of square bracket is square bracket squared over 2. We did that. Antiderivative Ra is Rax, did that. Pick up another constant Ma, and I just said I'd tidy it up. 72 over 2 is 36, 72 over 2 is 36, and I can keep this equals here, or else I can maybe just do something like that. Okay. This here we can see that because most of the load is on the right of the beam, that Ra and Rb add up to, so the reaction here and here add up to the total load. But because most load is here, Rb will take more than half the total load. Just a small thing to look out for if you want to see does your answer make sense. It's simply supported, which means that Ma is 0, and that's the case for simply supported. I would still write this because for fixed ends and cantilevers, it's non-zero, and you don't want to get into the habit of not writing it. Write it all the time, and if it's 0, set it equal to 0. And we said the other thing was that the bending moment here was 0 at 6. So the bending moment at 6, we substitute x equal to 6 into this, and we know we get out 0, and that's how far we are. And I think it was at this point I realized I wasn't actually pressing record, or I hadn't pressed record. So and I was actually giving out to you about don't put 6 minus 5 into your calculator, but sure, I didn't press record. Anyway, so square bracket of a positive thing is itself, so this 6 minus 2 is 4, 4 squared is 16, by minus 36 plus 36. This is square bracket of 1, which is 1. 1 squared is just 1, so it's plus 36 by 1 is 36. So that's minus 540. And of course, you want to say Ra will be positive here. Ra times 6 is 6 Ra. And this is equal to 0. So to solve it properly, add the 540 to both sides. To get 6 Ra is equal to 540, and to get rid of the multiply by 6, divide by 6. So we'll divide both sides by 6 to find that Ra is equal to 90, and it's kilonewtons. And we might just say, let's look at the total load. 3 meters of 72 per meter, that's 3 by 72. Half that load is 108. We would expect this to be less than 108, and indeed it is. So that's a good little check. So this yields, oh, that's all done then there. So just putting the m of x back together, minus 36 square bracket x minus 2 squared plus 36 square bracket x minus 5 squared plus Ra, which is 90x, and Ma is 0. That's where we are. And now what we have to do is solve EI times second derivative of deflection equal to this. That's on the next page. Okay, so I think I'm going to write that up the top. So the equation to solve for part 2 is EI, hopefully you can see this, yeah, times the second derivative. Now again, the notation is important. Like in my opinion, if you don't have the notation right, you might be confused, you might know what you're doing, you're going to be making mistakes. Try and get it right, is basically my opinion, or my advice. Equals to, what is it equal to? The bending moment. Let's just write that down. It's minus 36 square bracket x minus 2 squared plus 36 square bracket x minus 5 squared plus 90x. Now the other thing I'd said when I didn't record was there's an or otherwise here. When you go into structural analysis next semester, you're going to go a bit faster here. You're actually going to write this down straight away. You're going to kind of get used to the pattern that if it's a UDL, it's minus the magnitude of UDL over 2 square bracket squared plus same crack, and then the RAX plus MA, and you'll know the MA is 0, and then you just have to go off and find the RA like this. Okay, so we want to solve for y of x now. What we have to do is anti-differentiate twice. So space is going to be an issue here, I think. So constant times function, fix the constant EI. Antiderivative of second derivative is first derivative. Fix the minus 36. Yeah, space will be an issue here. Antiderivative of square bracket is square bracket squared is cubed over 3. Plus fix the 36 square bracket cubed over 3. Fix the 90. And then the antiderivative of x, which is x to the 1, is x squared over 2. And we pick up a constant, which is C1, which is proportional to the slope. And for we'll just look ahead to what does the deflection look like. Now, obviously, the beam doesn't look like this. This is exaggerated. Well, unless it was a plot of, I mean, it mightn't be that exaggerated if it's millimeters and meters. Anyway, look at the slope there, it's negative. So C1 for simply sport is going to be negative because the beam looks like that. Right, where are we at? Up here. Now we anti-differentiate again. Come over to the left here. Fix the constant. Antiderivative of the first derivative is the function y of x. Minus 36 over 3 is minus 12. Antiderivative of square bracket cubed is square bracket to the 4 over 4. 36 over 3 is 12. Antiderivative of square bracket cubed is square bracket to the 4 over 4. 90 over 2 is 45. Antiderivative of x squared is x cubed over 3. Antiderivative of C1 is C1 times x. Because if you differentiate this, you get C1, fixed constant, and the antiderivative of x is 1. So you get C1 times 1, which is C1. And then we pick up another constant. But this other constant is proportional to the deflection at 0. This is always going to be 0 in Math 7019. Now, if you do your cantilever fixed on the right-hand side at x not 0, that's not the case. Just don't do that. So this is what we have, tidying it up. Now this looks a little messy. It's really EI times y of x, 12 over 4. 45 over 3 is 15. Bingo bango. So we've got the y of 0. So this is the deflection. Here is 0. That gives you the C2 is 0. And now you have to use that. The deflection at 6 is also 0. So if we sub x equals 6 into both sides, we'll get something useful. So off we go. EI times the deflection at x equal to 6 equal to minus 3 square bracket 6 minus 2 to the 4 plus 3 square bracket 6 minus 5 to the 4 plus 15 times 6 cubed plus C1, which is what we're looking for now, times x, which is 6, and sure, C2 is equal to 0. There's no point writing that down. Now, look at the picture. What is the deflection here? The beam does not deflect here. It can't, like, deflection is when it goes below then this distance here. It can't do that here. Deflection at the span for simply supported and indeed fixed ends is 0. So what that means is that this thing is equal to 0. So I have EI times 0, anything times 0 is 0. So you get 0 is equal to this. Now I'll just write the 0 over here instead. Right. Now let's use our calculator. Now all the things in the square brackets here are positive. So they're just like square bracket of 6 minus 2 is square bracket of 4 is just 4. So I have minus 3 times 4 to the 4 plus 3. Now look, 6 minus 5 is 1. Do not put that into the calculator. 1 to the 4 is 1. Do not put that into the calculator. 3 by 1 is 3. Plus 15 by 6 cubed. And I end up with 2475. Now remember, you're thinking my C1 times 6 is 6C1. I want my C1 to be negative. So if I take this away from both sides, I get 6C1 is minus 2475, and now I divide both sides by 6. And notice, like, there's no mess. The reason there's no change in the signs here is because the opposite of multiplying by 6 is not dividing by minus 6. It's just dividing by 6. So that's why there's no issues with signs when you're multiplying and dividing. Don't forget this number here now. So I'm just going to, there's a negative anyway. I'm going to divide by 6 here. 825 over 2. And then what you want to do is put your thing back together by, you want to get y of x on its own. Like when you have a differential equation like this, the job is to find y as a function of x. You don't want the EI there, so divide both sides by EI by multiplying by, I might just write this down. So dividing by EI is the same thing as multiplying by 1 over EI. That's not that weird. If you want to divide by 2, multiply by a half. Are they the same? Divide by 2, multiply by half. They're the same thing. Divide by 3, multiply by 3, same thing. So that's how you do it to both sides. And you can, if you want, you think if you're dividing by EI here, but it works the same, whatever you think of it. Put it back together. Oh, there's that, there's that, there's that. And then C1 times x. C1 negative times x. And C2 is 0, so no need for that. And then I just plotted it. Now it's kind of hard to see, but because most of the load is under, like there's twice as much here, it's slightly asymmetric, but it's very hard to see. But bingo bango, there you go. Oh, maybe there's some things we should write. The deflection here is 0, and the deflection here is 0, and wherever the maximum deflection is, the slope is 0. Well, there's a few more things we can write actually. So the slope here is equal to 0, and we should write that the slope here at 0 is negative because it's going down. So that's everything for simply supported.